Okay, so welcome to this next video. In this video what we're going to discuss is non-homologous end joining, okay, which is a method that the cell has for repairing double-strand breaks within DNA, okay. Now, for short, non-homologous end joining is often abbreviated to NHEJ for short, okay. So this is a mechanism for repairing double-strand breaks within your DNA. Now, it's the most common mechanism used to repair double-strand breaks within your DNA. However, as we'll see, it's not perfect. It doesn't actually return the DNA to what it was prior to the damage, basically. It does lead to a mutation, basically. It leads to a permanent change in the sequence of nucleotides within your DNA, okay, often anyway. So, what we're going to start off with is discussing the double-strand break for the starters, okay. Then what we're going to discuss is the way that the cell detects the double-strand break, okay. So we're going to look at the detection of damage to DNA, okay, and then what we're going to do is look at the machinery that's going to repair that double-strand break, specifically the machinery for non-homologous end joining. So there are other ways of repairing double-strand breaks in your DNA, okay. The other main way that you can use to repair double-strand breaks is homologous recombination, okay, and that's a better way, but it's less commonly used by the cell, okay. So there are two main ways to repair double-strand breaks. We're going to study this one, non-homologous end joining. Okay, so let's start off with what is a double-strand break. Okay, so if we have our DNA here, okay, so these two parallel lines here, these represent two complementary strands of DNA, one here and one here. Okay, so a double-strand break is going to be a cut that goes through both of the strands, okay, and completely severs this piece of DNA into two, okay. So what can happen is ionizing radiation often causes double-strand breaks. So we'll have some sort of lightning bolt coming in here to represent our ionizing radiation, okay. So high-frequency electromagnetic waves, such as gamma rays and X-rays, count as ionizing radiation. In addition, beta particles, which remember are just electrons flying around, those count as ionizing radiation. And also alpha particles, which remember consist of two protons and two neutrons. They're the nuclei of helium atoms. Those are also a form of ionizing radiation. Okay, so some sort of radiation comes in and damages the DNA, okay, and this is going to result in a double-strand break. So what's going to happen is both strands are going to break and the whole piece of DNA is going to split in two. Now, often it does not break as cleanly as I have shown here. But what I've shown here suggests that both pieces have broken at exactly the same level, basically. Okay, so we have a clean break. We don't have any overhangs on these two pieces here. That's often not the way that it actually happens. So let me show you what's more realistic in reality. Okay, so if I draw a bigger picture of my DNA, let's put some organic bases here just to illustrate the point. So I'll just make these up. Okay, so let's have these 5 organic bases here. Okay, then we'll have the complementary ones here. So the complementary organic base to adenine is thymine. The complementary organic base to thymine is adenine. The complementary organic base to cytosine is guanine. Okay, and just finish it off there. Okay, right. So now let's say we're going to suffer a double-strand break here. What might happen is we might break this nucleotide off completely. So we might break it off here and here, okay, and this nucleotide is going to go flying off, okay. We also might break the DNA here, and let's say also, where else should we break it? Here, okay, and then we'll cut this one out. So what will we then end up with here? Well, we'll end up with these two strands, and what I'm trying to show you here is that these double-strand breaks are rarely clean in the way that I've just shown you here. Okay, so if we look at what's on this side, we'll have the adenine and the thymine here. Okay, then we'll have the thymine here. Okay, and then on the other piece, we've lost the adenine here and the cytosine here. I'm cutting out these ones. These have got completely obliterated away by the ionizing radiation, so they've flown off somewhere. Okay, and now our other fragment, the other side of our double strand break, we're going to have this guanine here, which won't have a complementary organic base anymore. Then we've got the guanine here, the cytosine, and then the cytosine and the guanine here. Okay, so what this picture is supposed to illustrate is that when you fire ionizing radiation at DNA, it makes a mess, basically. It doesn't usually end up cutting it cleanly in half perfectly like what I've drawn here. Okay, usually you get these overhangs on either side. You might get nucleotides that have just gone, basically. They've been blasted off. Okay, so it's rarely clean, basically. Okay, so that's another thing that we're going to have to deal with. Okay, and this is one of the reasons that when we religate these two strands together, we're potentially going to lose organic bases from this portion that was hit by the ionizing radiation. Okay, for instance, if you imagine, what if we lost both of these two nucleotides here? Imagine for a moment that we lost adenine and guanine. That entire dinucleotide got blasted off. Then we would have completely lost this base pair, and there would be absolutely no way we could have known what was there. Okay, so that illustrates nicely how we could completely lose this information here. Now, homologous recombination, okay, that's another way that we can repair double-strand breaks, and that has a way of getting around this. Okay, but in the case of non-homologous end joining, we can't get around that, basically. We're going to lose some organic bases, potentially. Okay, right. So this then is a double-strand break. This is how we have produced our double-strand break, our damage to the DNA. Now, for short, double-strand breaks in the DNA are often abbreviated to DSB. So D for double, S for strand, and then B for break. Okay, right. So what we now want to talk about is firstly the detection of double-strand breaks, and then we'll look at the machinery behind non-homologous end joining, which will try and repair this double-strand break. Okay, so we want to turn our attention to the machinery that's going to detect the double-strand break firstly. Okay, now I'm going to go back over to using a cheaper picture to show the DNA, because drawing this will take a lot of time up each time, but what I'm going to do is now acknowledge that the double-strand break might not be clean in this way, and I'll show some overhangs. Okay, so we might have an overhang there, and you know, these overhangs might be in completely the opposite direction, they might not be complementary overhangs. Here we had complementary overhangs. We had an overhang in this direction on this strand, and an overhang on the opposite strand on the other one. Okay, but these overhangs might be on the same side, and the reason that would make sense is because the radiation's come in from this side, so you're more likely to get nucleotides blasted off this side than you're going to get them blasted off this side. Okay, so often you'll get double-strand breaks that look like this. You've got overhangs on both on one side, and then nothing on the other side. Okay, right, so here is our double-strand break. So, the first thing that's going to come and bind to double-strand breaks like this, or to exposed ends of DNA here, okay, so that's what it's specifically going to bind to, these exposed ends that we've got here, okay, is something known as the mRN complex. Okay, so this is the first thing that's going to recognize the fact that there is a problem here. Okay, and you'll understand why this is called the mRN complex in a moment when I show you the free proteins that are going to make up the mRN complex. Okay, so let's show our double-strand broken DNA now. Okay, so I'm going to look now just at one of these fragments. Okay, the same will be happening on the other loose end here as well, but we're just going to focus on one. Okay, but remember the exact same thing will be happening on the other. Okay, so this complex is going to come down and associate with this loose end here. Okay, and this is going to consist of 3 proteins. So let's highlight these up. So, The first one is going to be a protein called MRE11. Okay, so we'll call this one MRE11. Now, MRE11 stands for meiotic recombination 11. Okay, so where should I put its name? I'll leave some space over here, okay, because I want to draw more things on there. So MRE11 stands for meiotic, because it's important in the process of meiosis, recombination 11. So the RE is for recombination, and then the 11. Okay, so we've taken M, we've taken RE, and we've taken 11. Okay, and that gives us MRE11 here. Okay, then, that's the M in the MRN complex. So this one contributes M to the MRN complex name. Okay, then the next protein down, which I don't know if I'll try and fit this in, is a protein called RAD50. Okay, so another protein involved in the MRN complex is RAD50. Okay, so this one contributes the R to the name MRN. Okay, and then finally the next protein is called NBS1. Okay, and this contributes the N down there. Now, NBS1 stands for Nijmegen breakage syndrome 1. Okay, so I'll write this down here. So the N is for Nijmegen, and then the B is for breakage, and then the S is for syndrome. Now, Nijmegen breakage syndrome is quite a rare syndrome that results from mutations in the Nijmegen breakage syndrome 1 protein. Okay, but it is rare. It's similar to ataxia telangiectasia. Okay, so we'll colour in Nijmegen breakage syndrome 1 in yellow here. Okay, so NBS1. And that gives us the N in the MRN complex. So this is the whole MRN complex now. The full thing that's bound here is the MRN complex. Okay, right. So, what then is going to attach onto the MRN complex? So we've got MRN complexes coming and attaching onto these loose ends, and both of the loose ends are going to get MRN complexes attaching on. Okay, then what's going to happen is the MRN complexes are now going to activate an enzyme. Okay, and this enzyme now is called ataxia telangiectasia mutated. Okay, so we're now about to meet ATM. Okay, so now we can understand why a mutation in this protein is going to give us a similar phenotype to a mutation in this protein, because actually they're involved in pretty much the same pathway. Okay, so this is named after the syndrome that is associated with a mutation in this protein, which is ataxia telangiectasia. Okay, so this is called ataxia telangiectasia mutated because it was first discovered as the protein which was mutated in people with ataxia telangiectasia. Okay, and it's often just abbreviated to ATM for short. Now, ATM is usually floating around inactive as a dimer. Okay, so let me draw one of these dimers here. So it's a serine threonine kinase, which I'll explore a bit more in a moment. Okay, and it exists usually in this inactive form as a dimer. So this is an ATM protein, and this is another ATM protein here. Okay, so this is what we can call the inactive dimer of ataxia telangiectasia mutative. Okay, right, so I'll colour both of them in this vivid purple colour as well. Okay, so here we have our first ataxia telangiectasia mutated, and it's not doing anything at the moment. It does have a little bit of enzymic activity, but you know, it's very slight. Okay, right, so it's totally, well, pretty much inactive at the moment. Okay, so what's it going to do once it is active though? Well, ataxia telangiectasia mutated is what's known as a serine threonine kinase, okay, which is an enzyme which is capable of adding phosphate groups onto serine and threonine residues within proteins. So let me just remind you of what a serine and a threonine residue is within a protein. Okay, so we'll start off with serine residues. Okay, so here's the amino group. So we'll draw the core amino acid structure first, okay? And we're drawing a residue, which means we're drawing the amino acid as though it's within a polypeptide rather than just the free amino acid. So here is the amino acid residue as it would appear within a polypeptide. You've got the amino group up here, the alpha carbon here with a hydrogen coming off it, and the carboxylic acid group here. Okay, now the R group of a serine residue consists of a methylene group, like so, with an alcohol group then coming off the methylene group. Okay, so this is a serine residue. Okay, and then the other type of residue that can be phosphorylated by serine threonine kinases is threonine residues. So we'll draw one of these now. So here's the amino group, here's the alpha carbon, here's the carboxylic acid group, so that's just the core amino acid structure. And now the R group of a threonine residue consists of a carbon still with an alcohol group coming off it and still with a hydrogen coming off it, but also it now has a methyl group coming off. Okay, so slightly different to serine, but only slightly. Okay, so this then now is threonine. Okay, so serine threonine kinase enzymes can phosphorylate certain serine and threonine residues within proteins. Okay, so let me explain what it means to phosphorylate a serine or a threonine residue. So we're going to stick a phosphate group on the side of the serine or threonine residue. Now I'll demonstrate this for the serine residue, but you can imagine that it will be almost identical for the threonine residue. Okay, so we'll firstly start off by drawing a phosphate group. So a phosphate group consists of a phosphorus atom double bound to an oxygen atom, then with two alcohol groups coming off either side. Okay, like so. And then a single bond to an oxygen atom, which has then acquired an electron via ionic means and therefore has a negative charge. Okay, so this is our phosphate group. Okay, right. Now, in reality, when you are going to add on a phosphate group onto a serine or threonine residue, you do not get it from a pure phosphate group like this. This is a free-floating, pure phosphate group that you do have within the cytoplasm, but you do not add them onto serine and threonine residues. Instead, what usually happens is serine threonine kinases take the phosphate group from an ATP molecule, the adenosine triphosphate, and they then add it on to the alcohol group of either the serine or the threonine residue. However, this will demonstrate the principle of what we're doing. Okay, so the principle of what we're going to do is we're going to bind this phosphate group onto the alcohol group of the serine or the threonine residue. Now, how can we do this? Well, let me circle this group here in purple, this portion of the phosphate group. Okay, so the phosphorus atom double bound to the oxygen atom with an alcohol group coming off. That has a very similar structure to a carboxylic acid group. Okay, in fact, if I turn that phosphorus atom into a carbon atom, that would be a carboxylic acid group. Okay, so this group, which is similar in structure to a carboxylic acid group, this can interact with the alcohol groups on these serine or threonine residues just like a carboxylic acid group would. Okay, so it can interact in a way very similar to an esterification reaction. So, what's going to happen then? Well, we're going to remove the alcohol group from the phosphate group. We're going to remove the hydrogen from the alcohol group of the serine or the threonine residue. Okay, we'll bind those two things together to make water, and then we'll bind the oxygen of the alcohol group of the serine or threonine residue to the phosphorus atom of the phosphate group. Okay, and this link here, which we've got, which is analogous to an ester link, this is called a phosphoester link. Okay. So we have performed a phosphoesterification reaction. Right, so it's analogous for the threonine residue as it is for the serine residue. Okay, so as I say, we don't usually do it just with a pure phosphate group that's freely floating in the cytoplasm. Usually we get it off an ATP molecule. However, the principle and what you end up with is certainly the same. Okay, right. So, these enzymes, serine threonine kinases, can phosphorylate serine and threonine residues on certain target proteins. So this is what ataxia-telangiectasia mutated is going to do once it's active. However, at the moment, remember, it is not yet active. It is in the inactive dimeric form. Okay, so how are we going to activate ataxia-telangiectasia mutated? Well, basically, once you have assembled an mRN complex here on the broken end of your DNA, what's now going to happen is an ataxia-telangiectasia mutated dimer can come and bind onto the NBS1 protein, the Nijmegen breakage syndrome 1 protein. Okay, so let's show this now happening. Okay, so ignore that red line here. That'll just have to make do. So invading that red line, here comes one of the ataxia-telangiectasia mutated enzymes within the ATM dimer here. Okay, and here is the other member of that dimer. So it's coming and it's binding onto the Nijmegen breakage syndrome 1 protein. Okay, and we'll colour it in once again in vivid purple here. Now, what happens when it binds onto the Nijmegen breakage syndrome 1 protein is it undergoes a conformational change, okay, that then allows it to autophosphorylate itself. So it's going to undergo a conformational change, and now this ataxia-telangiectasia mutated enzyme, that is the one that's actually bound to the Nijmegen breakage syndrome 1 protein, this can then autophosphorylate itself. Okay, and it's going to autophosphorylate itself on a serine residue. Okay, so that's the process of activation then now. Once it has phosphorylated itself like so, what will happen? Okay, so this pink blob here, this is representing a phosphate group. Okay, and because it has phosphorylated its own residue here, that's called autophosphorylation. Okay, so auto, remember, means self, okay, and autophosphorylation therefore means self-phosphorylation. So ataxia-telangiectasia mutated will self-phosphorylate itself, and once it has phosphorylated itself like that, the other member of this dimer, the other one that's clinging on here, this will detach off. Okay, so this one will go off now. And this one is the one that's now active, the one that's got the phosphate group added onto it and which remains bound to the Nijmegen breakage syndrome 1 protein. Okay, right. Now, this ataxia-telangiectasia mutated enzyme that we have here that's now active is going to phosphorylate certain proteins. Okay, and these proteins are going to be part of histone cores within nucleosomes. Okay, so I just want to now talk about histones a little bit so that we can understand what ataxia-telangiectasia mutated enzymes, once active, are going to do. Okay, but I think we'll actually take a break here and do that in the next video.